Hello, algebra class. Welcome back. We are continuing Unit 11 radical stuff. So we are on the day 2 notes, and we're going to do a little bit of everything. So the first part is perfect squares, which we've already kind of dealt with. So be on the lookout for perfect squares so that you don't have to do factor trees. Save yourself the time. While 121 is a perfect square, you cannot square root a negative. If you remember, you can't have a negative under the radical, so this would be undefined or no solution. For something like this, number 2, square root of 4 is going to be 2, square root of 100 is 10, and then you can reduce that. 2 over 10 reduces to 1/5. You can always do math frac on your calculator. For number 3, you're going to end up with square root of 81 is 9, square root of 49 is 7. That cannot reduce, so it's just 9 over 7. Something like this, you got 2/3 times the square root of 36. Square root of 36 is 6. And then you can multiply that together. You get 12 over 3, which is 4. So being on the lookout for perfect squares, it's a lot quicker than having to do a factor tree for every single one of these numbers. Square root of 100 is 10, so 5 times 10, you're going to get 50. 6 times the square root of 4 is 2. 6 times 2, you're going to get 12. 3 times square root of 49 is 7. You get 3 times 7, you get 21. And then 4 times 8, because square root of 64 is 8, you get 32. All right, so nice and easy when it comes to perfect squares. All right, radicals, we did these, radicals with variables, we did these yesterday, or 2 days ago, I guess, last video. We're going to take these, remember with radicals, you just divide by 2. You're finding out how many pairs there are. 10 divided by 2, you're going to get 5. 8 divided by 2, you're going to get 4. And there's no leftovers, so there's no need for a radical. Square root of 4, that's a perfect square, that's 2. 4 divided by 2, you're going to get 2 with no leftovers. 9 divided by 2, you're going to get 4. That would make 8. And then there's 1 left over. The 1 left over stays under the radical. Something like this, the square root of 20, you're going to have to do a factor tree. You get a pair of 2's and a leftover 5. So the pair of 2's goes on the outside. I'm going to leave a little bit of space because I know I'm going to have some variables here. And then the leftover 5 stays under the radical. Square root of x, that's the same thing as x to the first. There's only one x, so that means there aren't any pairs at all. Since there aren't any pairs at all, the x is just going to stay under the radical. 3 divided by 2, that's going to give you 1 pair with 1 left over. So the 1 pair goes out front, 1 left over stays under the radical. And then with z, 12 divided by 2, you're going to get 6 with no leftovers. And that's going to be your answer. For the next one, if you're going to multiply what's inside the radicals together. Remember our rules with multiplying. So 20 times 4 is 80. This is still under the radical. X squared times x to the third, if you remember those rules, when you're multiplying and the bases are the same, you add the exponents, so x to the fifth. And then y times y to the 10th, same thing as y to the first times y to the 10th, you'll get y to the 11th. And now you can do a factor tree with 80. So you could do like 8 times 10, 2 times 4, 2 times 5, 2 times 2. So we can circle our pairs. We've got a pair of 2's, another pair of 2's, and a leftover 5. The pairs go on the outside. The leftover 5 stays under the radical. I'm leaving a little bit of space because I also have variables to deal with. 5 divided by 2, you're going to have 2 pairs with 1 left over. 11 divided by 2 is 5 with 1 left over. And then I can multiply those 2's together. I get 4x squared y to the 5th and 5xy. So there's that. For number 5, same idea. M to the 3rd times m to the 5th. You're going to add those. You get m to the 8th. Y to the 10th, y to the 11th is y to the 21st. And then you divide them by 2 to see how many pairs there are. 8 divided by 2 is going to be 4. It's even, so there's no leftovers. 21 divided by 2 is going to be 10 with 1 left over. So the leftover stays under the radical. For this one, you could multiply 2 times 16. That's one option. Another option is you could notice that square root of 16 is a perfect square, so you could turn that into a 4. It's your call. If you want to just multiply them together, 2 times 16, you're going to get 32. X to the first times x to the first is x to the second. Y to the third times y to the second is y to the fifth. And then from there, if you want to do your factor tree, lots of 2's. So you're going to have two pairs of 2's and a leftover 2. So the pairs go on the outside. The leftover stays under. X squared divided by 2, you get 1. Y to the 5th, 5 divided by 2, you're going to get 2 with 1 left over. And I can multiply those 2's together. I get 4xy squared, square root of 2y. All right. Multiplying radicals, we did this the other day, and then we'll get into some of these squaring radicals. That'll be kind of new. So for multiplying radicals, remember you multiply the outside number with the outside number, inside number with the inside number. So like for number 1, the outside number here technically is a 1. 2 times 1 is 2. 4 times 20 is 80. Now, if you wanted to, kind of a shortcut with this one that I just realized is square root of 4 is a perfect square. So really, this is the same thing as saying 2 times square root of 4 is 2. So really, we're saying 4 times the square root of 20. That's going to be a little bit shorter of a factor tree to have to do. So this ends up being 4 root 20, and you just do your little factor tree. All right, if you wanted to multiply those out and do a factor tree with 80, you certainly could. But I always like to look for perfect squares if I can. Pair of 2's is going to join the 4 out in front, and the leftover 5 stays under. So you end up with 8 root 5 for your answer. For this one, multiply the outside numbers together, you get negative 20. Inside numbers, 27 times 3, you're going to get 81. Now you could do a factor tree, but 81 is a perfect square. Square root of 81 is 9. And then it times it by negative 20, you're going to get negative 180. Makes it much shorter. Let's go to the next page. When you are multiplying a radical by itself, you could do 2 times 2 and say, oh, that's a square root of 4, and then say, oh, that's a perfect square, that's 2. You could do square root of 3 times square root of 3 and say, oh, that's square root of 9, but that equals 3. Any radical times itself is going to be that number. All right, square root of 3 times square root of 3 is going to be 3. Square root of 2 times square root of 2 is 2. Square root of 8 times square root of 8 is just going to be 8. Don't bother multiplying them together and then figuring it out. Just go straight to the end. Square root of 10 times square root of 10 will be 10. Square root of xy times square root of xy will be xy. Square root of a squared b times square root of a squared b is going to be a squared b. All right, so what happens when you multiply a root by itself? You get what's under the radical, or under the root. You get what's under the radical. All right, so keep that in mind as we do these problems. So this is going to be 2 root 6 squared. This is the same thing as 2 root 6 times 2 root 6. So we're going to multiply the outside numbers together. 2 times 2 is 4. And then root 6 times root 6, keep that in mind, we're doing the same thing that we were just doing. Root 6 times root 6 is 6. And then 4 times 6, that's going to be 24. Much quicker than having to do 6 times 6 and then potentially do a factor tree. For this one, you got negative 2 root 6 times negative 2 root 6. Whatever is being squared, you write it down twice. Negative 2 times negative 2 is 4. Square root of 6 times square root of 6, you get what's under the radical, 6, and you get 24. This one's a little bit different. Notice the only thing being squared is what's in the radical, or what's in the parentheses. So the only thing being written down twice or being multiplied twice is this root 6. So we're really doing 2 times root 6 times root 6. Well, root 6 times root 6 we know is 6. We still have a 2 out in front. 2 times 6 is 12. So you got to pay attention to what's inside the parentheses and what's being squared. The next one, we have negative 2, and then we have square root of 6 squared. So square root of 6 times itself. Well, once again, square root of 6 times square root of 6 is 6. We have it times by negative 2 this time, so you get negative 12. This one, the whole thing's being squared, so you're going to do 4 root 10 times 4 root 10. 4 times 4 is 16. Root 10 times root 10 is just 10. And then multiply those together, you get 160. All right, so these should be nice and easy just because we don't have to do any factor trees, which is really nice. This one, you got negative 4 root 10 being squared, so negative 4 root 10 is being multiplied by itself. Negative 4 times negative 4 is positive 16. Root 10 times root 10 is positive 10. And then multiply those together, you get 160. For number 7, you've got square root of a that's being multiplied by itself, and then the 9 is just kind of out in front. Any square root times itself is going to be that number or letter in this case. So square root of a times square root of a is a, times 9, or just 9a. This one you got negative 9. You got square root of a times square root of a. Once again, square root of a times square root of a is a, times by negative 9, you just get negative 9a. And the last one, you have negative a root b times negative a root b. Negative a times negative a will be positive a squared. Root b times root b will be what's under the radical, b. So it's just a squared b for your answer. All right, so that's pretty much everything with radicals. The next time we do a video, it'll be kind of a summary of everything. So that's it. Thanks for listening.